Computers sometimes need to do arithmetic with rational numbers. But depending on context, different representations may be more appropriate. There are no perfect solutions. Floating point numbers corner the niche of fast, inexact calculations, being extremely fast, particularly with dedicated hardware, and spanning many orders of magnitude. As for computations that require exactness and high precision, most solutions involve storing rational numbers as fractions, putting large or arbitrarily sized integers in the numerator and denominator. An alternative idea for storing exact rational numbers has been floating around for a while, but not really picked up. One using continued fractions, and their lesser-known cousin continued logarithms. And we explore the basics of how that would work in this video. Full bibliography is at the end, and citations are inline, but I'll reference by name the two papers where these ideas were invented and extended, by Bill Gosper and Thomas Brabeck, respectively. Here are some examples of continued fractions. Fractions with fractions in their denominators, which have fractions in their denominators. They don't seem particularly helpful, but they have many useful properties. I'll use this notation for the rest of the video to describe continued fractions. Simple continued fractions, where the numerator of each fraction is 1, are represented with just the list of their integer components. Generalized ones, with variable numerators, require two lists of numbers, numerators on the bottom list. Each rational number has a unique simple finite continued fraction, and most useful irrational numbers have recurring continued fractions as well, like the ones on screen. But how could you possibly do arithmetic with these? Well, continued fractions lead with the most significant terms on the left. You can, moving left to right, generate progressively better fractional approximations of a continued fraction. Each term gives more information. Let's do a worked example with e. Let x be e's continued fraction. Now, consider this expression. A, b, c, and d are constants. Suppose you were to remove the first term, 2, from x. For this expression to represent the same value as before, we must replace x with 2 plus 1 over x. Simplify, and we have this expression. Now, we have a generalizable method to ingest from a continued fraction. Let's plug in some initial values for these constants and give it a try. Notice how both a over c and b over d get progressively closer to e. And it kind of makes sense. If the remaining less significant part of e, represented by x, turns out to be infinity, e will be a over c. And if it's 0, b over d. As we keep incorporating more terms, the amount the remaining terms can influence goes down. Because e is irrational, we just keep approaching it. E is always between a over c and b over d. We can use this to calculate fractional approximations of 1 over e also, or 5e minus 1 over minus 2e plus 15, just by changing those coefficients. This algorithm also works for finite continued fractions. When you exhaust all the terms, you ingest infinity, in a way the last term of any continued fraction, which works out to setting b over d to a over c, for the continued fraction now represents a over c. There's an answer. But we are not limited to generating fractional approximations. We could actually yield a continued fraction representing our expression. We can egest terms to y just as we ingest terms from x. So let y equal our expression. We know no matter what x yields next, the value the expression represents must be between a over c and b over d, supposing neither c nor d is 0. If a over c and b over d have the same integer part, when we rewrite them as a mixed fraction, we know that it must be y's next term. We can therefore rewrite y as term plus 1 over z. We reassign y to z and egest the term. To keep the expression up to date, we first subtract the term from it, like this, and then reciprocate it. See the example on the screen. Interestingly, the generation of a fractional expansion can actually be viewed as a series of matrix multiplications. Start with a coefficient matrix, and for each term t you ingest, multiply it by this matrix. Egestion can also be viewed as a matrix multiplication. You multiply by the inverse of the matrix for incorporating a term, equivalent to this. You still need two integer divisions to test whether a over c and b over d have the same integer part, and what that integer part is, which is still expensive. So far, we've only considered ingesting from simple continued fractions. However, we may want to ingest from generalized continued fractions too. Some constants, like pi, lack a periodic simple continued fraction, but have a periodic generalized one, or, like e, have generalized equivalents to their simple continued fractions that converge faster. Thankfully, there is a way to ingest generalized terms. The algebra is a little different. It basically works out to this matrix multiplication. The fractions produced by this method are not always fully simplified, unfortunately. We can leave them or simplify them. Either way, it's an extra expense in space or time. Still, we can calculate pi's continued fraction indefinitely with this algorithm, limited only by integer precision. Cool. But what about if you wanted to do arithmetic with two continued fractions? Say, adding e to pi. We can generalize this procedure to allow for arithmetic calculations with multiple continued fractions. To use multiple continued fractions, we use this expression. First, here's the algebra of what happens when you ingest x and when you ingest y. We can visually frame this by considering each coefficient as a vertex on a cube. We view this face of the cube as being the one x is ingested into. We multiply each coefficient on it by the ingested term, and add to it the coefficient opposite it. We also push the original values of this face onto the opposite face. We do the same with y, but this face instead. Egestion is much the same. We subtract from every coefficient on this face its corresponding coefficient on this face, multiplied by the egested term. To determine the egested term, we must get the integer parts of all four fractions, a over e, b over f, c over g, and d over h, because both x and y can vary independently between 0 and infinity. Unfortunately, the coefficients will get large very fast, around a digit every other egestion, and there's not much you can do to keep them down, so you'll need some big integers, quadruple-digit bit precision maybe, to handle particularly precise computations. Now, you're not just limited to arithmetic. For calculating square roots, or more generally, solving an equation of this form, you can apply Newton's method to find the root. Gosper explains this in detail in his paper and goes through a worked example. Okay, this is pretty cool. The implications of this process are interesting. Unlike, say, decimal arithmetic, here you move left to right with increasing granularity when doing arithmetic. And this means that, theoretically, you could chain together input and output streams of continued fraction terms to do more complex things. Precision can be increased arbitrarily and after the fact, and things can be evaluated lazily. It's pipelined. Of course, this means it's unsuitable for many kinds of computations. You'd never use this in place of floating point numbers. Still, there are many use cases. You can do complex arithmetic processes with this approach, just by chaining together the machines we looked at. You could compute trigonometric functions by using the continued fraction expansions of the functions and calculate an interesting, potentially important operation, like, for example, this one, to high precision with a layout like this. Cool. Unfortunately, there are several prohibitive drawbacks. This arithmetic process is very slow, most egregiously relying on integer division. Computer hardware isn't really built for the structure of this arithmetic. There was an IEEE proposal for continued fraction hardware in 1983 that, as far as I know, never got picked up. And how large should these continued fraction terms be allowed to be? Leading terms can, for some physical constants or conversion factors, reasonably exceed the limits of a 32-bit or even 64-bit integer. Consider Avogadro's number, or the Planck constant. But most terms won't be that big, so how big should the term size be? Also, certain arithmetic statements can't be evaluated under this model. Root 2 times root 2 equals 2 cannot actually be calculated. The machine just fails to output, the fractions approaching 2 from opposite directions. Gosper suggests an eager egestion model, where if the machine fails to egest, we force it to. and then if it fails, potentially retract some of the terms with negative terms. But he doesn't make particularly rigorous how we would do this. Those are enough issues to sink the premise. However, anticipating these issues, Gosper coined an alternative structure more friendly to computation, the continued logarithm. Gosper specified the simple binary continued logarithm in his manuscript, a binary string, the only terms ones and zeros. So when I refer to continued logarithms here, I refer specifically to binary ones, although there are generalizations for other bases. Like a continued fraction, the most significant bits are on the left, and each bit corresponds to an operation or matrix transformation. We can also phrase a continued logarithm as a run-length encoding of the binary string. This continued logarithm would be this. A computer would probably not store the continued logarithm like this. It does not improve our arithmetic protocol, but this arrangement is useful because it lets us see how the continued logarithm corresponds to the continued fraction. This continued logarithm corresponds to the following improper continued fraction. This identity is sometimes a useful way to view a continued logarithm. In fact, it's called a continued logarithm because each value in the run-length encoding is the integer part of the base 2 logarithm of the remaining part of the continued logarithm. I feel I should emphasize that 1 and 0 are arbitrary names. You can think of 1 as meaning increase the order of magnitude, and 0 as analogous to starting a new continued fraction term, because that is kind of what it represents. Anyways, let's convert a number, say 17/15, to a continued logarithm. A 1 indicates the number is greater than or equal to 2, so we divide by 2, and 0 indicates it's between 1 and 2, so we subtract 1 and reciprocate, keeping it greater than 1. We stop when the number is infinity, leaving us with the continued logarithm. Let's watch. Converting this continued logarithm back to a fraction is also similar to how it's done with a continued fraction. Going back to the 2D arithmetic expression from earlier, y equals ax plus b over cx plus d, when a 1 is ingested, to maintain y's value, we must double a and c, or halve b and d, because x has halved itself. When 0 is ingested, first x reduces itself by 1, meaning we must add a to b and c to d to maintain y. Then, we account for the reciprocation by swapping a with b and c with d. These operations correspond neatly to the below matrix transformations. We use the identity matrix to convert the continued logarithm back to a fraction. But like with continued fractions, we can use a different initial matrix to get, whatever, this for example. Note here that, as with continued fractions, we're just applying matrix transformations to input stuff. We can use the same algorithm to output a continued fraction. But why do that when we could more easily output a continued logarithm? If a over c and b over d are greater than or equal to 2, y egests a 1, halving itself by doubling c and d, or, if possible, halving a and b. If they're both between 1 and 2, y egests a 0, decrementing itself by subtracting c from a and d from b, then reciprocating itself by switching a with c and b with d. Implementing them requires only bit shifts, compare, subtraction, and swap. The comparison test similarly requires only compare and bit shift. Like continued fractions, we have a three-dimensional generalization with the same nice properties. Each logical operation, addition, swaps, whatever, need only happen along the edges of the cube. Amazing. And, like with continued fractions, you can do things like apply Newton's method or generalize into even higher dimensions. Unfortunately, most nice continued fraction recurrences don't apply to binary continued logarithms. However, you can mix and match how you input and output terms. You can input continued fraction terms, even improper ones, and output continued logarithm terms. This way you could, for example, use the regular continued fraction for e to generate a continued logarithm on the fly for e. These continued logarithms have several practical advantages over continued fractions. They require only very basic functions to ingest or egest, and, as each one represents a binary order of magnitude, a run-length encoding is unnecessary. Continued logarithms can span many orders of magnitude, and terms are literally a bit. This in contrast to continued fractions, which do have an equivalent to the binary string encoding, the Stern-Brocot tree. And while this tree does have useful and interesting properties, and arithmetic is possible to do on it, its precision is clustered awkwardly around 1/2. Continued fractions don't have a reasonable way to deal with them, requiring massive terms. Like continued fractions, under this scheme, each rational has a unique finite continued logarithm representation, each irrational algebraic an infinite one. Everything can be represented given space. And further, the length of a continued logarithm representing a particular number seems to scale roughly with how complex it is. Basically every number you could reasonably want to represent can be represented exactly with under 200 terms. A big improvement. This simple continued logarithm scheme doesn't handle numbers less than 1. However, it can be pretty easily extended by recognizing reciprocate and negate as terms. We avoid redundancy by only permitting them to be leading terms. That way, numbers less than 1 can be transformed immediately into numbers greater than 1, but not the reverse. However, this still does not solve the problem from earlier, that certain expressions just cannot be evaluated under this scheme. We still cannot evaluate root 2 times root 2, cannot even adjust one term, because the fractions just approach 2 from different directions. So we may need to introduce some form of redundancy so that we can eagerly adjust and then maybe retract some terms to evaluate these expressions. While Gosper does not particularly flesh this purposeful redundancy out, another researcher did. Thomas Brabeck proposes, in speculatively redundant continued logarithm representation, a set of 8 terms to comprise a continued logarithm, the matrix transformations they correspond to, the range of values where they can be applied, and what they transform values into. Only 3 bits to specify a term. Not bad. 4 of these terms are non-speculative, meaning we know the terms will not be retracted. These 4, 1, 0, reciprocate, and negate, we've already covered. Brabeck proposes a speculative decision procedure, still using only elementary operations. If it can't be that all fractions satisfy one of the conditions, see if they satisfy a more limited version of the conditions. If they do, we can adjust one of the 4 speculative terms, which may be retracted later or approved. Consider a matrix we are trying to pull a term from. We can only attempt egestion if the fractions in the matrix are all well defined, no zero coefficients in the denominator, as with continued fractions. If the fractions we are looking at are all negative, obviously negate them first. If they're less than 1, reciprocate them. If they're between 1 and 2, subtract 1 from each and then reciprocate them. And if they're greater than 2, halve them, all unambiguously pushing the fractions towards termination. So cool. But what if we can't unambiguously say any of that? Well, then we use speculative terms so that we at least say something. The 4 speculative terms, 1 underscore, 0 underscore, reciprocate underscore, and 1 underscore underscore, have respectively the same matrix transformations as 1, 0, reciprocate, and 1, but they are permitted to be used on wider domains. If we at least know the fractions are all between 1 and 4, we adjust 1 underscore, which lets the resultant fractions be between 1/2 and 2. Between 1/2 and 2, we adjust 0 underscore, potentially causing some fractions to be positive and some negative, what Brabeck calls a singularity. Same goes for reciprocate underscore, adjusted if the fractions are between -1 and 1. If there is a singularity, a 0 underscore or a reciprocate underscore adjusted recently, and the magnitudes of each fraction are greater than 2, we can adjust 1 underscore underscore to move their magnitudes closer to 1. Otherwise, like before, we just have to wait until one of these conditions is satisfied pending more ingestion. Brabeck really leans into the matrix composition idea to show how speculative terms, while being the same operations, imply different things about what the matrix coefficient fractions can be, producing different intervals. The important bits are that a 1 underscore underscore implies that a singularity, caused by a 0 underscore or reciprocate underscore, is ongoing, because 1 underscore underscore operates on split intervals. Anything else would imply that the speculation had resolved, and either a new one had started, or no speculation was ongoing. The nice thing about the speculative redundancy is that, while misspeculations will occur and intermediate values may have to be retracted, with a reciprocate typically, it will not fail to compute anything. This speculatively redundant scheme, according to Brobeck's testing, which I have not myself corroborated, was both significantly faster to output and generated only slightly longer strings on average. As for root 2 times root 2, this scheme still cannot just say 1, 0, but it can at least eject some terms. What you get is this unending speculation, which just approaches 2 from above, because 0 followed by an infinite string of 1s is just 0. Better than failing to output, at least, and you can cut it off arbitrarily. That's it for the math. There's a lot I did not get to cover, and I highly recommend further reading if you're interested. I pulled most heavily from continued fraction arithmetic, and on speculatively redundant continued logarithm representation of the IEEE Transactions on Computers Volume 59. Lots more in both than what I just summarized. I recommend them if you're interested in learning more. Finite Precision Number Systems Arithmetic is a good book if you want to read more about computer arithmetic in general, good companion piece to these two. There have also been more recent hardware proposals for continued logarithms. I linked all the ones I could find. However, as far as I know, there is yet to be a real proof of concept for continued logarithm-based arithmetic, hardware or software, so this is all theory. And part of that is probably that there's yet to be found a problem for which this is clearly a solution. It's very cool, and has some theoretical advantages, but there has just not yet been cause to use it. Actually, I've been thinking about a GPU-based continued logarithm system. As arithmetic is pipelined, requiring only elementary operations, perhaps you could do some massively parallel arithmetic with them. No new hardware, only some compute shaders repeatedly operating on massive textures. Was considering attempting a basic proof of concept, but ran out of time and patience immediately, so I've cited a paper with some very parallelizable arithmetic problems you could have a go at implementing if you were interested. The math adjacent to this area is also fascinating. The Stern-Brocot tree's cool properties were what got me down this long rabbit hole. Maybe in the future I could cover some of that math. If you're interested, there are also several pure math extensions of continued logarithms I found online. I haven't really read them, but they seem like good places to go if you want to explore the mathematical properties of continued logarithms beyond their arithmetic applications. That's about it. Thanks to the contest holders for the push to make a video. Definitely wouldn't have been made otherwise. Good outlet to get this math off my chest. Hope you enjoyed.